Our next speaker is Simon, who's going to change things up a bit. We won't be talking about single sign-on for the first time in 45 minutes. And instead, we'll talk about person identification through Gait.
Hello. I think now it's okay. Sorry. So for those who don't know what Gait is, it's our walking patterns, and from those we can identify people. And we care about that because we want to build anonymizations in the future. And this paper is all about understanding the problem and why does this process work. Now, to begin, why is Gait important? So Gait patterns are all over us. So we walk every day, and it's also captured a lot. So we have video captures, but we also have something like accelerometers which capture Gait. And then we have these new devices like virtual reality, augmented reality devices that capture our Gait in very precise manner. And we also get something like motion capture suits who are now rolled out to consumers and give us very detailed information about the motions and therefore also about Gait. And we looked at Gait in a bit in an abstract way. So we have this data here on the left. Oh, can't see it. Okay. So here on the left picture shows how we look at Gait. So we don't look at the visual information. We only look at landmarks on the body and then the motion itself. And our research question was, what are the features in Gait which make it identifiable? How much do they contribute to the identification? Do the Gait recognition systems we have today work with the same feature set that we see that human observers use? So there's been a lot of work in psychology. They looked at how do humans recognize people from their Gait, and then, of course, what would we need to anonymize Gait in the future? Now, our methodology for that was first that we looked at the studies we already have from psychology. So they have been working on that for quite a while. And from that, we extracted suitable features for us and then built perturbations which remove these features from the data we have so that we can, on one hand, have the feature alone, for example, just the head, and then the rest of the data without that feature. So we then can compare how the recognition works on that. And then in the end, we trained a recognition system on this modified data to see what precision we get on that. Now, the features we selected, we made two distinct categories, which are like opposing categories. So we have macro and micro on the left side. And then below you see the features we took from the literature. So for macro, for example, we have the step length, walking speed, and the cadence. And then for micro, the small asymmetry and variability in the Gait trajectories. And for those, we built perturbations, which you see below. So for example, for macro, we remove the variations from the trajectory of the points. And for micro, we remove then the trajectories themselves and only keep the small variations. And for example, then we also remove body parts from the data, while for micro, we kept only those body parts. And then we have two more categories, which are static and dynamic. Static are the shape and general body layout of a person, and dynamic are the things that change over time. And for example, for static, we then looked at the static pose and resampled the data to have less frames. And for dynamic, we only looked at the motion and removed the overall shape of the person. Now, I'd like to show you some examples of that. So this is the clear data. So this is how the data originally looked like. Then, here's without the head. We actually kept the head in there because for machine learning, it's useful if it stays the same dimension. But we set all the points to 0. Then here's just the head. But you can still, I think, recognize a little bit that someone is walking. So at least from the pace. And then a few more. So this is coarsening macro. You can see that we removed much of the precision of the points. And then this is our motion extraction. So we removed the overall shape. You can't recognize that it's the person anymore, but you can still see that some points are more important than others. They move more than the others. Yeah. Now with this data, we fed it into a machine learning system. So we actually had a data set from HostFL with 57 people. For each person, we had 20 gait cycles, and then we did a classification of identity and sex of that person via a support vector machine. And the training was always performed on the perturbed data, so on the data as you saw it before, so that the machine learning system can then find if there's still identifiable information in there. Okay, and so for each, we then performed normalization and normal PCA, and then did regular machine learning flow. Now, for the results, this is micro versus macro. So here on the left side, in white, you see it's a little bit hard to see because it's all at 100. You see the performance for the clear data. So the clear data was always at 100%. So it was very easy to recognize people. And then you see for the macro, in the first part, it's where we removed individual body parts. And you can see that for all body parts that we removed, actually nothing happened except for the legs. So the legs contain some information that's not available in the other body parts. And then when we only look at the body parts alone, so the micro features on the right, you can see that the head scores the lowest. It's a little bit under 60%. And if we look at the legs alone, they alone achieve 100%. So they are enough alone to identify someone from that data. So we can already say, okay, the legs are the most important. It's not super surprising, but still interesting to see. And then when we look at our other macro and micro features, we, for example, can see that most of the macro features still achieve 100%. Only if we coarsen really a lot of the information, then it drops a little. And we see also the same for the micro features, except when we really coarsen, so we only keep the lowest digits, the two lowest digits, or the lowest digit of the position data, then of course we can't identify anyone anymore, and it goes down to chance level. Now, moving on to dynamic versus static, we can see that for the dynamic features, all of them still stay at 100%. And when we look at the static features alone, it drops a little bit, so it's not as good as the dynamic part of the information, but still very identifiable. And then moving on from that, we used these features and combined them to see, okay, when we now remove multiple of them, what happens? So this is what you can see here. Now, the individual techniques we used are in the paper, and I don't want to go into detail on them now. But what you can see is that even if we combine multiple techniques together, the identification rate is actually still quite high. So if we, for example, look here on the right, we see that if we combine micro and dynamic features, they still score 100%. So there's still most of the identifiable information. And when we look at the others, while it goes down a little bit, we can still see that none of them really reach chance level. So even removing two parts of that means that it's still identifiable information. And while here we look at the identification, we also looked a little bit at the utility and did a user study with some people and showed them the data and showed them how the data looked like after the perturbation, and found that most of them destroy the utility quite a lot. So using these single features, it's actually quite hard to remove the identifiable information from the data. So we're already coming to my takeaways. So these simple gait perturbations mostly fail to anonymize the data. This is because this data is actually very complex. So, of course, the position of my hand depends on the position of my arm, of my elbow, of my shoulder, and so on. So all these points are connected. And while it maybe looks like it's very high-dimensional data in the beginning, actually, if you do a PCA on that, you only need 4 PCA components to capture about 96% of the variability in there. So it might look at first it's very high-dimensional data, but it's actually can be reduced down a lot. And the dependencies then make it very redundant in there, so that the identifiable information is hard to remove. So we see a strong indication that we need a holistic approach, that we can just remove single features from the data, but we really need to either perturb all data points in a way that makes sense for gait and walking patterns, or we need to really generate new points at all. And the dependencies that we must consider here are like the temporal dependencies. Of course, it's the time series, so each pose is dependent on the poses before it. And then, of course, the physiology of the person is also very important. So this concludes my talk. Now open for questions.
Okay, well, we have plenty of time for questions.
Hi, thanks. What about the temporal sampling frequency? Does that matter? Is that part of the coarsening also that you considered?
So, for example, this is what we removed for the static features. We essentially removed the temporal component by using the first pose of the sequence or an average pose over all of them, and you still get 80-90% identification rates. So it doesn't really matter so much. It matters a bit more than the dynamic features, which contain more information, but still it's very high.
Hi, thanks. This was super interesting. Can you talk a little bit more about the difference between how humans and computers can draw conclusions from what they see? Because this is so intuitively to us that, this is identifiable. But can you talk a little bit more about the differences there, if you have any?
Well, we took the features from the literature of human perception of that, but we then didn't. So we would also have to go the other way around, that we take the features that we have from the machine learning and see if humans can make sense of it, to see that they also work for humans. So we can say that the features we found for humans also work for machine learning, but not the other way around. We haven't tested that.
Okay, we do have a Zulip question. The question is, what do you think about group identification, i.e. people from the same country or the same age using Gait?
So far, we tested some, if you can get the age of a person from the Gait. That didn't work super well. We didn't have any data on country-specific groups, so all the data sets are not super big, and they're all from one university and then the same students, so it's hard to tell. Would be interesting to see if there's really differences in gait patterns based on ethnicity and maybe cultural dependencies in there, but we don't know.
Just out of curiosity, how much of human gait recognition was based on actual gait and not the, say, height or face of the person they were looking at? Were you able to distinguish? Or?
So for the dynamic features, we removed, of course, then as I said, showed before, where you only had these moving points, which removed the overall shape of the person, so you didn't have the dimensions of that. But of course, a person with long legs will make bigger steps, so it's still implicitly there. The connection between height and the motion itself is still there, so it's hard to remove. I'm not sure if it helps to see if only removing the height would do us any good. I think we really have to look at all the points and try to perturb them in a way which makes sense for walking and for walking of a person that has a similar shape.
Okay. In the interest of time, I think we'll move on. There is one question on Zulip if you want to take a look at that after the talk. So our final speaker for this session is Pratyush, and he's going to tell us about time-deniable signatures.